morning, everyone. Welcome. Happy Friday. We will start soon. I hope you have had a good week. We are discussing the topic of classification, and we started this on Monday. And so this will be our third part, and we'll continue next week with the same topic of classification and kind of use the time to look at broader methods within classification. So today will be part 3, and we're going to be looking at a particular or two classification methods called linear discriminant analysis. That's what the LDA stands for, and Naiive Bayes. And there is relationship between them. And this is also related to your assignment 5, the last problem. And so for several reasons, it will be an important topic to cover. We are going to go back to the book for this discussion, and what I will make reference, and I would want you to know, for the last lecture we had, we went somewhere else and we've got some other discussions to do, but we'll come back to, by the book, I mean the book ISLR, Introduction to Statistical Learning with R. And section 4 and 4.4 and 4.5 is where this thing is covered. The person you see on the right in the slide today is Thomas Bayes. He is a statistician, and this discussion we will have today is based on a contribution he has made. And you probably have encountered him in one of your probability classes back in the days, or you might have encountered him in other occasions too. Sometimes I wonder how smart these people were. He lived in the 1700s, 1701 or something, and then lived for some years, came up with that clever idea of manipulating things. And so sometimes I admire those people at that time. And the picture I found about him on Google, what else? It looks like that. And that gave me an idea for how they looked. And this is a classical picture. And what I have on the slide on the left is to just make that connection and get ready for a warm-up question for the day. And I promised last time, this is going to be a fun warm-up question. The warm-up question last Wednesday was a very interesting one. I should applaud you. I should commend you for how well you're doing in terms of paying attention. It is not an easy thing to do when things are done online. And I hope the suggestions that you gave each other for what you're doing to stay focused and pay attention will be something you could use. I was impressed by the list, and I looked at the numbers. It took me some time. It was a busy day, but I had the post-class announcement late in the evening. We found, I saw from what you told me, and that was a good sizable class who attended. I don't know, 80% or so, or even more of the class would give themselves a 10 or a 9, when 10 is absolute perfect attention and 9 is the next best thing, and so on. Nobody said 1, nobody said 2, and so on. So those numbers were I was very happy to see. So keep doing what you're doing. That was something serious. Well, to some degree, something serious, but the warm-up question for today is going to be fun. And it's also Friday. I didn't forget that. And it has to do with classical. And Brit will be the person to write the warm-up question for the day. Let me say it, and you'll try to find a way to say it. What is your all-time favorite classical work you read, listened to, or watched? And so all options are there. It could be a book, it could be music piece that you listen, or you keep listening, or you've listened, and it's your absolute favorite thing to do, or is your all-time favorite, or it's something that you watched. By watched, I mean it could be an artwork, or it could be a movie or a documentary. But the thing that is about it is classical, and that's what I'm trying to represent here, okay? So Brit, when you're ready, write it. What is your all-time favorite classical work you have read, listened to, or watched? Okay, that could not have been any clearer. So thank you very much for a good job. Go ahead, participate. While you do that, I'm going to stop sharing, and I'm going to tell you what I have done. You have been patiently waiting for feedback from me on your project proposals, and I have told you that everything that I was reading was a go. There was no place where I say no go, so almost everywhere. But I wanted some of you to have a little bit of an adjustment, or a little bit of composition of a team, or a second option that would have been better than the first option, that type of feedback. So I have given you, and those are now on Blackboard. The project proposal is not graded because you haven't done any work yet, but If you are approved, you get 100. And so in that sense, you would see those 100, which is nice to see. So all of you who have submitted and your project proposal is approved will have gotten 100. For some of you, I have written very brief thing to just say your project is approved. For some of you, I have actually talked to you during office hours this week, or on when you have requested some other time. So you have more detailed feedback from me. For some of you, I have given some feedback, but it is kind of brief, but still a useful one. So if you go to Blackboard, you would find that feedback, or personally for you. But I have also collected all the teams that we have and put an Excel file, which is what Chris will do now. Chris is going to take us to Blackboard. He has been warned, so I hope he is listening to me. So you take your screen and take us to Blackboard, and I will point the Excel file where that is available, okay? So we go to this place, we go to projects, that's where it is. And so we had two before, and now I added it. The one on the top is the project team list. If you could click there. And now it's going to ask you to download and open, and I'm sure you are familiar with doing something like this. And so we will hopefully get an Excel file come up. Perfect. So this is not nicely done. I will improve it and make it look better. But what I have done with help of Helen is just find what you were saying and then, list the teams on the left and what project title they currently have. This is just a rough indication of what you're saying right now. It could be tweaked, it will be refined, it will tell exactly what you have done. So the first thing to note is that there is something like 36 of them. This was about the number I expected, but I also wanted you to know there are some teams that are of 2, the ideal number. There are some teams that are of size 3 because the project is large, and there are some teams for one reason or another, a person is working alone, but it may not stay that way. They may find a teammate later on. So this is a complete list that you probably would benefit. First, make sure that what I have said about what your team is doing is right. I might have made a mistake, so make sure that it is right. Secondly, know what others are doing. We'll get a chance at the end of the semester to hear from others and things like that. But I don't think it hurts to know how, what kind of projects are happening in the class now, and maybe there could be some synergy. Oh, we remember that linear regression discussion we had, and interaction and synergy. There may be some, and so it's good for you to have an idea of where how the projects look like. So know its existence, go check it, and see what others are doing. What I will do, and while we are here, because I have you, Chris, you can go back, just close this one, and I will continue talking about projects. Go back there and go to course content, and go to lectures. Okay, so this is kind of not nice, but we've got an organization, right? Every day has got a folder. So if you go to today's date, you will find slides there, okay? So the slides are there. So I have saved myself one point from, having to discuss this in my chat analytics after the class is over now. So if you go there, the slides that we are discussing today are there, except for Naiive Bayes or Bayes' photograph. It's not there, but the rest of it is there. So I think this is enough. This is what I wanted to show you on Blackboard. And let me come back to the project topic. I'm going to have meet with everyone. I have said this before. I want to repeat. I want to talk with each team before you really get into your projects. And that will happen next week. So I'm going to have a sign-up sheet and put it on a Google Doc or something like that, like what we did last time, for you to help you find teammates. And there you will write among those, times that I would say, teams that would work for you. And I will meet with every single team for a few minutes to see where you are, if I have a little bit more guidance to give or something like that. For some of you, it would also mean, that first meeting will also mean to meet with, if there is a mentor, like there are a couple of projects, a good of them, 3, 4 maybe, that have picked with the health data visualization, like the guest lecture Dr. Amram gave. And so I would like you to meet him and to have a discussion, get access to data. And there are also a few other projects like that, where there will be a student of mine or Professor Amram or somebody else that might be useful to have in that conversation. And so I may need some time to work out things that would work, but I will make you sign up for those, and we will talk. If you have talked to me and if you've got everything that you need, go ahead, go get started. So next week will be a time for doing that. And most likely it will be sometime out of the normal work day, maybe after 5 or so. I don't mind doing that, but we'll try to find some time. It's going to be a busy week for me, but I'm sure we will find a way to get as many of you as possible talk to next week. Don't forget your assignment 5. It is due on Friday, and I'm going to get back to screen sharing, and we will start discussing today's topic. While I do that, let me see if you have anybody has got any questions. You can unmute yourself and ask. Let me see how things are going on.
I just had some internet issues. Did you say when we would be signing up for the individual meetings?
I will put up a Google Excel file on like I did last time, and I will ask people sign up here when you would like to meet. If there is anybody who's got a good idea for how I could get this done, so that I have, I could wait till my office hour and people would come in and so on, but that's probably not enough. 1.5 hours is probably not enough. Plus, I would rather have people know when they're coming and instead of waiting and things like that. So if anybody's got a better suggestion, let me know. But what I'm thinking of doing is put an Excel spreadsheet type of thing where you will sign up for times that you could meet, and then I will schedule. That's what I say. Any other questions? Okay, so we're back here, and I'm going to go start. So do we see the right thing? So somebody could show me something here. Somebody who has got a camera on. Brit, can you give me a thumbs up if you're seeing the right slide? Yes. Okay, so what we did on the first 2 parts when we talked about classification was the first day we looked at logistic regression, along with having an introduction to what classification problems are and things like that. And the second method we looked at, which was the last lecture, was k-nearest neighbors. And so we're going to see two methods that are going to be added to our catalog, and they will be better related with logistic regression than they are to k-nearest neighbors, and we will see the distinction and why they are being introduced in a moment. So there is some weaknesses some logistic regression has for some kind of problems, and or combinations of things where discriminant analysis is an option, a better option, and there is something that would make naive Bayes even a better solution for some kinds of problems. So that's what we are trying to do, and this has to do with distributions more than anything else. Okay, and our discussion about naive Bayes is going to be relatively short. I'm going to warn you, so I'd like to finish as much as possible what we will see today, and there will be slides where there will be math. I have told you, and you have said, one of the ways in which you keep yourself paying attention is taking notes. Take notes, but you may not have enough time to kind of write down what is on the slides. You don't want to do that. The slides are there, so you can come back and look at them later on. So if you see a slide where it's heavy with math equations displayed, just got comforted that you can go back to those slides and look at them later on. So it should not be a big problem. Okay, so I would go slowly, but every time I need to rush up, or in a way, and rely on the fact that you can go back, understand that. So Bayes, Thomas Bayes, his theorem is going to play a central role both for linear discriminant analysis and for the method that bears his name, naive Bayes. The naive there, by the way, is naive as you know it in English, because there are other ways in which you could use that same fundamental theorem in more sophisticated ways. In fact, you can tag on lots of things to the basic approach. So naive is not his first name. It's his first name is Bayes or Thomas, and so this is a way to say people, and it's probably not the best way to say it because it's not really that naive, quite frankly, but that's where it is coming from. So there is, we'll display the equation in a moment. There is something to be said when we have mathematical relationship that we can express one way or another. Usually they would be equivalent. So you're saying this thing is equal to this, and so this working around is where the benefit of this method is going to come from. And the method that we will look at would work when we have normal distributions for each class. And when we have normal distributions, what we would get will be called linear discriminant analysis. And depending on which level we go to, it could also be quadratic discriminant analysis. But what we will be discussing is not necessarily, we will talk about normal distributions, is not necessarily limited to normal distributions. It could be extended. But what we will do, and what we will make something linear discriminant analysis, is the assumption that the distribution is normal. Okay, so what does Bayes' theorem say? And this is the slide we will spend a little bit of time on, and I try to help you by color coding things. And so get settled, and we'll go through this. We're looking at a situation or relationships between, just like every other time, between input and output. Our input is X, our output is Y. Our input, we will show them when we're thinking about vectors, which is generally the case with a big capital X and a big capital Y. And when we have a specific value to talk about, we will use a small letter case. Because these problems we are looking for, or the whole idea, what we are discussing is classification, our response will have one of discrete values, right? It is not a continuous value. We have discrete values, classes, labels, and so we'll have a few of them, some number of them. And so whenever we say, y equals to k, we means one of these labels. Whenever we say big X equals to small x, we mean among the inputs that could happen, this is the instance we have chosen. That's what we mean. So, and we're looking at conditional probabilities. So the probability that y gets the value k, given x is a particular x we have chosen, this probability can be expressed. This is a conditional probability, something given something. The something first is y equals to k, and what is given is x equal to x. This is equal to the product of two terms. The probability of x equals to x, given y, we're flipping things around if you haven't noticed, y equals to k times the probability that y is k divided by the probability that x is x. So if you were to kind of imagine for yourself now, take the product of whatever is on the left with the denominator and what is on the right, then you will see those things are flipped around, okay? These things have names, and these names are good to know, and I will tell you what they are called, and then we'll have a shorthand notation for just the equation I just explained now. So the first thing we want to give a name for is the thing that we are calculating, the thing on the left. That's called a posterior. That's what we ultimately want. That's the probability of the given response with a given set of predictors, our desired thing, the posterior. On the left, or on the right, we have a bunch of things, three things. So we'll walk one at a time. We'll start with the thing that's yellowish or goldenish color. That is the probability of the response overall, the probability that y equals to k. That's the probability of the response overall, and that's called a prior. So we've got posterior, we've got a prior. What you have at the first term in the numerator, the blue term, is likelihood. That's the probability of the given predictor values, of the predictor values given the response. So what is flipped now is what we ultimately wanted, is the response given the input. And now we are going to take it the other way around and then say, what is the input given this response? What is the likelihood that we would see this response when we have this input? That's the first step. So it's called likelihood for a good reason. The probability of the predictor getting that value given the response. The thing on the denominator is called the prior. And that's the probability of the predictor values itself. So both of these yellowish or goldenish and the purple are both priors. One is prior as the probability of the response overall. The other is the prior as the probability of the predictor values overall. Okay, so we've walked through this, and these things are equal, and this was discovered in 1700 by Bayes. And what we will do now is make use of this probabilistic relation, or this relationship between things where we have flipped around to our advantage, where our predictions are going to come by what we will do by looking at distributions. So we're going to give a name. We're going to rename the thing that we was in blue, the likelihood. We're going to have a shorthand for it, and we'll call that f sub k of x. And that is the shorthand for the probability of x equals to x given y equals to k. And this is, if you think about it for a while, and we'll see a picture to help us see it, that's the density. That's the distribution, and that the density for x in class K. The subscript for f there is the class that we're looking at. That's the density. Whatever is multiplying it, it used to be on the right, now it became on the left because it became a scalar value. The golden thing is that we will call it a pi k. That's a multiplier now, is the marginal or the prior, which we have defined. So when you look at it this way, now the numerator is clearly about density, and there is a multiplier for it. That's the marginal or the prior probability for that class K. And notice how the K's are talking to each other. So we are looking at K, and which is what we are trying to use, the posteriors, the thing that we are ultimately interested in. What are we dividing it by? We're dividing it by everything that can happen. And so we're looking at all the, each one of the labels. So the K now has shifted to capital, if you haven't noticed. So we are looking at all of the classes. And so the FL now is a distribution. We've defined what F means. So we have a shorthand. So the only difference between what you see in the blue and what you see in the purple is that the K, instead of being a subscript K, which is exactly the response that we're looking at all of the possibilities. So the L is ranging from 1 to capital K, and we have multiplied it by the same thing. So what you are seeing is now a quotient, something that looks like, okay, there is something here, and it is being divided by everything else added together. It looks more like a proportion, right? And it makes sense now if you think of it that way. Okay, so the shorthand is not just a shorthand, it also exposes what we are trying to do, and how, and we'll see in a second, this could be estimated from empirical values, data sets we have, not necessarily working with the distributions, and that's not probably easy for you to see now, but when we get to the next few slides, you will be able to see. Okay, so if we now have seen the expression that you saw, which would help us to make a decision, that's called a boundary, the ratio that we just saw now, and we've got distributions like this. One thing is, and so the pi's now are these priors, as you have seen them, and we have two distributions, and they have exactly the same value. Pi 1 and pi 2 are exactly equal, 0.5. Then we have a decision boundary that looks like what you see on the left. And so everything now, when it is to the left of the dotted line, this is called the Bayes boundary, which is the expression you saw in the previous slide. Whatever I have written here, it'll be a number, and it will be a number, actually something that would tell you which way you would go. And so everything to the left of this will be green, everything to the right of it will be classified as pink when you see these distributions. You will have a hard time when it comes exactly at that boundary, and there is no other way other than to flip a coin, or you make a decision, or you break tie one way or another. But otherwise, the distribution gives you a guidance for when you will call something green, when you will call it a purple. This is when the pi's were exactly equal. When they are not, then you could see how you will favor. So the distribution now has got the boundary, as you see on the right, it is shifted. And so we've got a higher chance of calling something purple rather than green because of the differences in the pi values that you see here. Okay. So then this is what all I have told you now is some probability relationships that Bayes has found by having to flip around, that you can make a quotient that will help you. So why now, how are you going to use this one and call it discriminant analysis, and why do we need it when we have linear regression to do classification that has got this probability that would stay within a range, that has fixed the faults that linear regression has in terms of being a useful tool for classification? If that was there, why do we need another one? We don't want to have more methods so that we have more complex things to know, to just add. There are places where it's unhelpful. So this three, in fact, is a very good summary, and I've wanted to write them in full so that you can come back and look at them. You can also read in the book if you wanted more explanations on each one of these. But what are the things that logistic regression could suffer from in linear discriminant analysis, which would be based on the probability relationship that I just showed you, would rely on? What are they? Logistic regression, when the classes are well separated. So you've got classes and they are kind of well separated, then the parameter that estimates that you would get, the betas in your logit function, they could be very unstable. So they are not going to be to withstand small changes. So as just a small number change could drastically change that, but it's unstable. Linear discriminant analysis does not suffer from that problem. That's one fix. So when we have classes that are well separated, so now you also would know, as you will build more and more intuition, some of you have a broader experience with machine learning algorithms, but when you see a problem, then you would know which tool would be a good candidate. Otherwise, you would waste your time trying it out. So that's one. When classes are well separated, logistic regression suffers from a problem that linear discriminant analysis would solve. The other is when n, how many cases you have, is small, and the distribution of predictors is approximately normal as you would know it, Gaussian, in each of the classes, then linear discriminant analysis is again better or more stable than logistic regression is. That will be case number 2. The third case, I know, now that I have seen your project proposals, there are some of you who are wanting to do classification that involves multiple classes. So you don't have one of two, but you've got many things to classify into multi-level classification. Linear discriminant analysis is popular when we have more than 2 response classes because it also provides low-dimensional views of the data, which we will see today. Here is the warning I gave you. There will be places where there will be a little bit of too much involved math equations. Don't get scared, come back and look at them. So this is the linear discriminant analysis when we come into it, when p equals 1. So you've got only one predictor. And so now the fk, the function, the shorthand I gave you a couple of slides ago, when p is equal to 1 and the distribution is Gaussian, there is nothing really that complicated about this. It's just a bit scary, but it's just a Gaussian distribution density function. And this is what it would look like when it is expressed in terms of the mean, the variance in each class. And the k that you see there is each class in your probability. So now that we have this Gaussian density function, our pk, the one that we would use Bayes formula to calculate, would take the form that you see on this slide. So there is no point for me to spend a lot of time just gazing at it. You have it, but you have understood the idea. The idea is the more important thing that you have. Otherwise, the only new thing that has happened now when we are looking at linear discriminant analysis when p is equal to 1 is that we have decided on a Gaussian density function. And this is the full exposition of what Gaussian distribution is, and here is what the formula would look like when Gaussian distribution is applied to it. Let's now look at an example. This is the place where I told you where that formula about Bayesian is turned from a density, a distribution function, into something that's about the data. What you see on the left is what density would look like. We've encountered this green curve and blue curve before, and the dashed line is your Gaussian or your Bayes boundary, where you will make a decision. Everything to the left is green, everything to the right of that line is purple, is how you would classify it. But you don't have that in data. What you have, if you were to do this analytically, of course, it will be like this, but that's not what this class is about. We've got data, and that's where predictions would come. So densities, generally speaking, not only here, but in other places, are replaced with histograms. This is where our data is turned, and we are trying to get these distributions come from the probabilities we would assign. We count things and things like that. So the green now, think of it as an approximation of it is obtained by the distribution that you see, the histogram that you see in green, and similarly the histogram that you see in pink. There are 2 things that are shown on the right. One is the dashed line that we have been having in the 2 or 3 examples of slides, plots, density functions I've shown you. So that is the analytical value, that boundary, that's the dashed line. And the solid line is what your distributions, the empirical value, gave you, and it is quite close, as you can see. And so if you go now left of that boundary is green, right of that is purple, you will be fine, except for a few places where you may have a few of mistakes in some ways. Otherwise, it's quite close. And so remember that. So the density function is now approximated by what you obtained from your data, and the more you have it, you will be better, because the histogram now will be finer and finer and look like the density function itself, but you have those values. And so what you see on the numbers there for the variance and the pi ones and so on is what empirically you have. And let me show you how distribution wise you have, and let me show you how you would estimate those parameters from the data that you have. This is another place where you would need to come back to look at it, but it's not all that difficult either. So pi k, which is this prior that we have defined, if you have data, then you would say how many of the cases, for example, if I had an actual data and I have said, here are students, here are staff, here is faculty and things like that, and I have a database, and now I'm going to turn it around and say how many proportions of them are students in this database, then I'll just count the number of students that in that database and divide it by the entire population rate. So I've got a number, and then I go count all the faculty, divide that ratio. Now I get, this is the prior for faculty, and now I've found a prior probability. Or if I come to this class and I would say here are computer science students, here are other engineering students, here are other students coming from biology, I could find a ratio like this and then say what is my probability of just calling up somebody and be right in terms of classifying them as a computer science student. You know what I mean? So that's what your pi k is, and now you have got your standard deviation and your means calculated from the data using these discrete values that you have obtained. That's what all this slide is saying. So when you have estimated them that way, you got the solid line, and when you have worked with a density function that you have assumed it exists, you will get the broken line. So that was linear discriminant analysis when P is equal to 1. In other words, when there is only one predictor. What would you do when you have more? Well, when you have more, you do more. And in this particular case, there is a case where P is 2. You've got two predictors, X1 and X2. And this figure is showing, it's a nice looking one, is showing you two cases. When on the left, when the two predictors have nothing to do with each other. They're completely uncorrelated, and you have the Gaussian distribution now looking like what it is looking now. It looks like the Seattle, I forgot its name. There's a nice place where you can go, and there's a garden, botanical or something like that, that you would see. It reminded of me of that picture. And what you see on the right is when these two predictors have got some correlation. In this particular case, actually is 0.7, if I remember the number right. You may find it in the book, and it kind of gets skewed. Otherwise, the theory we have developed, everything that we have said would carry on just fine for larger ones. And this is a case when you would see a visualization. I'm not going to spend time on this one. When you have two predictors and there are three classes to look at. I would rather spend more time, a little bit more time, on Fisher. Fisher is the person we met. So we met him a couple lectures ago, or maybe even more than once. He's the guy who did the classification of the flowers, the iris flowers, and into three classes. And he found a good way to do that is by looking at petal lengths and petal widths, sepal width, lengths and sepal widths. And those were excellent ones to actually be able to do classification. And so the scatter plot, you remember it, except now it is now colored maybe slightly differently. And so there are three classes, setosa, versicolor, and virginica. And here is the scatter plot that shows you. What he did, other than, he did a number of things, but one of the things he did, and I think it bears his name, is to show how linear discriminant analysis could be used to classify this with these predictors, but also the power, I told you a few slides ago, where linear discriminant analysis for multi-label classification, which is what this one is an example for, is good way to visualize. So there are three classes here, and here is a way to visualize them when you do the discriminant plot, as it is called. And so you've got three classes. It will always be one, or if you have k classes, the plot will have k-1 dimensions. And we had three classes here, and so it will be conveniently shown on a two-dimensional plot. I should watch out my time. And we're doing fine. And if you are not following me along and with 110% attention, speak now. Let me see if there is anybody who is not following me with 10% attention. Anybody? I'm going to check the chat session, see if there is any volunteer to tell me they are not following me with 10% attention. So silence means everybody is following with 10% attention, or it's not 10%. 10 attention, 100%. Okay, great. So this is the plot where you see there were 3 classes, and you see on a 2-dimensional plot, and you can see now the 3 classes clearly separated. They were not that clearly seen when you had to look at them from the scatter plot. You could see in some places where the predictors were a good indicator for how things are clustered, but here it comes in a good way. And this one is a result of linear discriminant analysis applied on them. By the way, this is a good time for me to tell you what's going to happen on Monday. So we've covered logistic regression, k-nearest neighbors, and today we are talking about linear discriminant analysis in naive Bayes. Monday's class will be a lab session. It happened to be on a Monday because I don't want you to forget what we talked, and so it would be better to have them in one session, and we will look at these methods, how they are done with help of code, and I'll this time also focus primarily on how they are done in R. So you will learn how to do that, and including how to get linear discriminant analysis used for a particular data set, as an example. Okay. I'm going to skip this. I don't think it's worth spending time on. Just like the Fisher example, we could also apply linear discrete analysis on a data set that we are familiar with. And that data set had to do with the credit card. And then there were different predictors, including whether the card owner is a student or not. And on that particular data set, linear discriminant analysis actually does a good job. And here is some of the results that you get when you apply it to that data set, which we have seen more than once. But I've got a couple other points that I would like to make with this slide. One of them is how you assess. And we did spend some time last time how to see true positive, false positive rates and things like that. And so a confusion matrix or something like this, where you would say the true value is yes and no in this case, for whether somebody is going to default or not, and the predicted one and the actual one is what you see in this table, and we've got numbers, and the diagonal is right, and whenever you are on the off diagonal, you're doing wrong. For this one, there is a 2.75 misclassification rate when you do linear discriminant analysis. So it's doing a pretty good job. And the rest of it is just a little bit of detail on how this method is working on this particular data set. But I wanted to show you that table also. This is a recap of the set of things that I've talked last time. What does it mean when you say it's false positive rate? What does it mean when it is false negative rate? And how you would use the things that you get with the use of linear discriminant analysis on this particular data set to help you get the values for this. That's what these ones are. So this is also my point to, as I said last time, to know how to assess how well a classification method is doing and the different metrics that could be associated. We've got many of them that could come out of those combinations of two things, right? Labels and predicted values, and what the diagonal values tell you, the true positive and true negative, and what the off diagonal values tell you. So this is a way, pictorially, to show how a method does on two of these metrics. When it is, typically the way it is done is a true positive rate versus the false positive rate. And so what do you want in terms of being false positive? You want it to be true positive, you want it to be high, right? The true positive rate is something on the diagonal that I showed you in the 2x2 matrix now, is the value there. And so that value, you want it to be high. And the false positive rate, you want it to be as low as possible. But your method could do some combination of these things. So the curve that you would get, what value of true positive rate you would get for what value of false positive rate you would get, is called an ROC curve. And you might have heard of this type of curve. So this is how you would show, after you have applied your method and you've got data set, what value combinations, because you're seeing them at the same time. Otherwise, you would just report one number. And that may not be a good indicator. And so if you also show, this is about sensitivity and specificity. Last time I've told you how they are related. So when you tell both of them at the same time, the curve that you would get is called an ROC curve. Is there anybody who knows what ROC stands for? I'm sure you must have seen it. Some of you, not all of you. Some of you might have seen it, but is there anybody who knows? Okay, I suspected you may. Oh, perfect. That's great. That is exactly right. Receiver operating characteristics is what it stands for, and it is historical because it was used in communications for the first time when it was used. So that's what it is. In machine learning, you also would want to talk about how good a method is by having this plot, and you want to be on the left uppermost corner right there. That's what your curve you would like it to be. And you could have different kinds of curves for different data sets, for example. There is another way in which you would say how well your method is doing by looking at the area under this curve compared to the diagonal. So the diagonal could be where you are starting off. And so the larger this area is, the better your algorithm is. And so you can give a quantity like that, and that is called area under the curve. That one is probably not so difficult to get what the abbreviation, why it stands for. Area under the curve, AUC. ROC, many people don't remember. I am impressed by Tyler knowing it, but it is not a common thing. So this just became a name, so how you would do it. So we looked at discriminant analysis, and we looked at linear, and there are other forms when it could get quadratic, and this just means what assumptions you're making about the distribution function and how extensions of it. Not probably too much of an important thing to spend too much time on. And so I'm going to go to Naiive Bayes. And so if you feel like I have cheated you because I skipped the slide, don't worry too much. Quadratic discriminant analysis is a generalization when you have extended some of these definitions. And this is just a pictorial way to show you. Naiive Bayes is what you will do to classify your Guardian articles, okay? And it is also going to be using Bayes' theorem, the flipping around of things. That same idea is used. But what it would do compared to Naiive Bayes, to linear discriminant, it differs from linear discriminant analysis, is that it assumes features are independent in each class. This is important assumptions. So in each class, the features are independent. When that is true, and when P is large, and there will be a slide where I will come at the very end, where I'll contrast all the methods we have talked so far, when one is good and when is something advantageous. Naiive Bayes is useful when P is large. And what is P? P is our predictors. In your case, is where you have a very good opportunity for something to be really big, what the predictors that you are going to be using. So when P is large, and then multivariate methods like quadratic discriminant analysis or even linear discriminant analysis would break down, that's where Naiive Bayes would use. Its assumptions are that the features are independent in each class, and it is useful when P is large. So for that reason, it would assume that this sigma k is diagonal, and now you see an expression for something that would be ultimately what your algorithm would be around. So your computation or your classification would be a computation of this value, right? So the sigma k now is proportional to the product that you see and the log of it. And when you do a little bit of math, you would find that you are talking about something, it's deviation from the mean, and then you're dividing it by the standard deviation and adding a term, and that is what the Gaussian Naiive Bayes formula looks like. Okay, so the assumption that is made here it's Gaussian, the features are independent, and it is useful when P is large. This method applies also when the feature vector is mixed. It's a mixed vector in the sense that you have got quantitative values and qualitative values. Just like that was not a problem when we did linear regression, it is also the case when we do Naiive Bayes. If you think about the assumption we just made, that features are independent in each class, it's fairly strong one because there could be dependence. But despite that strong assumption and the simplification that came because of that assumption, Naiive Bayes often does a good job classification, including your articles. And for that reason, it is used in practice. Okay, this is my last slide. And we're doing fine on time. So logistic regression, linear discriminant analysis, and Naiive Bayes are the three methods we looked at in this series of lectures. If I include k nearest neighbors, which is of a different flavor, there is no probability or anything like that associated with it, then we had seen 4. But these 3 are related, and so contrasting them is worthwhile. So logistic regression is very popular for classification when there is 2 things, when k is equal to 2. Linear discriminant analysis is useful when n is small, or the classes are well separated, and when Gaussian assumptions are reasonable. This is also useful or successful when k is greater than 2. Naive Bayes is useful when p is very large, like you have. We will on Monday look at cases where we will see examples of code when these methods are compared to each other and how they are seen. But if you want to read ahead, then section 4.5 in the book would be a good place to start. We will not just use exactly that same, but we'll find a way to cover all the methods we did in one class. And this is the place I would like to stop and see if anybody's got questions for me. I can stop sharing. Or if you have questions, I can go back always to the slides, but let me stop sharing and see if anybody's got questions for me. Okay, be ready to sign up when I put up the Excel sheet on a Google document, and I will see every single one of you in one of those meetings. If you wanted to think further with your projects, you should get started, and I assume most of you have already started thinking about what you will do. But that conversation is going to be important, especially for those of you who are going to need data set access or something like that. Okay. All right, if not, then take care, and I will see you all on Monday.